So, welcome to the second video in the Learn Machine Learning and Deep Learning series. And today we will be talking about machine learning linear models and loss. This is the second video in the series, and this will be a shorter video. However, stay tuned. And today we're going to be talking about linear models and loss. Please make sure to subscribe and drop a like, and let's get started. So last time we talked about the idea of a linear regression and classification, but today we're going to jump a little more into linear regression. And we're going to start off by talking about what are linear models. What's a linear model? A linear model is simply when we fit a regression line to a certain data set of x versus y. There's single linear regression, there's multivariable linear regression. And what's going on here is that we're basically fitting a line to a certain data set so that in the future we can make completely new predictions based on this regression line. So as you can see in this data set, we're comparing cricket chirps per minute on the x-axis versus temperature in Celsius for a y-axis. And what's going on here is that in the second graph, what happens is that a regression line has been inserted or fit to this data in order to create new predictions, such as for the temperature 125 cricket chirps per minute, where there's currently no data point or example, we can predict what the temperature for Celsius likely would have been. What's the equation for a linear model? Although this video series is more developed for a conceptual understanding, it's also important to recognize the technical facets behind linear models. So let's break down this equation. So the equation goes as y, the output is equal to the beta naught plus beta 1 input I plus epsilon I. So let's break this down. Our output, or what the equation is equal to, is the dependent variable. This is our label. This is the label or y of the example. And so basically what that means is that in the xy pair, this is the output. Beta naught is the population y-intercept. You can basically think of in the y equals mx plus b analogy, this is our b. Then beta 1. Beta 1 is a population slope coefficient. This is basically our slope. xi, or input, the ith input in this case, is our independent variable. And so when we sum these two components, the component of beta naught plus beta 1 xi, this is the linear component of our linear model. And then on the side you see this extra term. This is the epsilon, the ith epsilon, or the random error term. And this is the random error component that sometimes makes our linear model not so linear. And the overall idea here is that this is basically the equation for a line. Simple y equals mx plus b, but in the long term we also have a little bit of a random error component. And what's going on here is that you can just think of any linear model or any regression line as the classic y equals mx plus b, a slope-intercept line. That's what's going on here. Let's move to talk about loss. So loss is really just how bad our example's model's prediction was on a single example. I've shown two graphs of linear models below. Take a second to pause and think which one has more loss. Well, it's pretty obvious. The one on the left is clearly more loss. Why? It's because for this model, the data points are much more farther from the regression line that's been drawn. Whereas for the linear model on the right, the regression model is much more accurate in that the line is closer and more closely clustered to the data points. So if we made predictions for the linear model on the left, where the regression line isn't well drawn, or well fit, then we're going to get very inaccurate predictions with very high loss or low accuracy. Therefore, loss is how well the line has been fitted to the data set. In other words, whether the overall distance or the square of all the total distances from a single data point to the line is actually not minimized, but actually inaccurate. Let's talk about why loss is really important in this discussion of machine learning. When we train machine learning models, we're training to reduce loss. The goal of all machine learning algorithms is to reduce loss. What happens is that we start by training the model. The next step is to check the loss every time we train it. And based on the certain loss, we update our model based on the parameters in order to reduce or minimize loss in the long run. So it's really this cycle of training, checking loss, reducing the loss up to the point you can, and repeating the process multiple times. Therefore, the process of reducing loss is highly iterative. It's just a cycle of checking step by step what's going on, how to reduce the loss, how you update the model, and how you train the model once again to reduce loss as much as you can. Like I said, this is a highly iterative approach. Going back to our original equation, this is a simplified version of the equation where output is equal to bias plus the weight times the slope. And in this case, the weight is the slope actually, and x is our input. So this is basically the classic y equals mx plus b equation, where the slope m is, in this case, the weight, the bias is the y-intercept, and x is our input and y is our output, like always. So the iterative approach for training linear regression or linear models is basically we start off with the iterative process. We have an initial guess of the weights and bias, initial guess for our slope and y-intercept, and we gradually or iteratively adjust these guesses until we find the weights and bias with the minimal loss. And thus, the broad idea in this scenario is to find the minimal loss point on our graph. So, I've talked about this process of being highly iterative, but it's also a process of just complete trial and error. We start off with our features. We put our features into a model or a prediction function, and we make predictions or perform inference, right? We compute the loss, and if our loss is not minimal, or we know we can do better, we compute the parameter updates and we feed it back into our function. So as you can see, it's a cycle, right? We put in both feature and label, and if our feature and label pair does not give us desired amount of loss, or the minimal loss, then we compute the parameter updates, we put it back into our model or function, and we try again. And it's really just a cycle. That's what I'm trying to get at here. That this process of reducing loss just comes down to trial and error, repeated thousands of times in our machine learning linear model. Now let's go into gradient descent, which is the actual learning process for reducing or minimizing loss down to its minimal point. What is gradient descent? Gradient descent is really just an optimization algorithm that's used to minimize some function by iteratively moving in the direction of the steepest descent as defined by the negative of the gradient. Okay, that sentence was a mess. Let's break that down. On a much more simplified basis, gradient descent is the process of finding the point where the loss is a minimum and converges. And to simplify it even more, gradient descent is how we get to the minimum of the loss versus weight graph. And obviously, the minimum of the loss is the most optimal. This is where our machine learning linear model is extremely accurate and precise, because we have minimized loss. As you can see in this three-dimensional graph, we're also looking for the minimum loss point in this graph. The way we perform gradient descent is that we basically adjust our derivatives or adjust our slope, which is our weight, and we find the weight or slope where we get to the loss minimal point the fastest and most efficiently. So, just like reducing the loss, gradient descent is completely iterative. We pick a starting point in gradient, or derivative, and we move down our loss/cost function. So let's go through an example. On the graph on the left, you see a loss versus weight graph. We pick a starting point, an arbitrary starting point, and we start with a negative gradient, since we're starting on the negative sloping side of the parabola. And this is obviously a very idealized version of a loss versus weight graph, because in the real world, these graphs look much more like this, or maybe in more higher dimensions. But this is a very simplified parabolic version of our problem. And so, like I said, we pick a starting point, we have decided on a negative gradient, and we're going to make our steps, step by step, iteratively. If you don't get what I mean by gradient, what I'm basically saying by gradient is slope. If you've taken a course in multivariable calculus, then you know that the gradient acts like a slope for multivariable functions. So when I say gradient, just think about it as a slope or how we adjust the weights, right? That's what the gradient basically acts as. And so on the graph on the right, we see how gradient descent works. We're basically moving down our graph, approaching the loss minimum points. So as you can see, we start at our arbitrary starting point and we make a step to the next point. And by doing this, we use a negative gradient. We're basically sloping negatively down the loss versus weight graph, or a cost function, and that's what's going on. And if you're wondering what this parabola actually represents in the physical situation, it basically represents the loss function, right? This is not the actual graph in the model, right? This is not the same thing as going back to the regression line, right? This graph simply represents the loss function. And when you think of the loss function, it's also really interesting to think of it as a cost function, right? That's why I say loss/cost function. Because in the real world, whenever we buy something at the store, whenever we make a purchase, we want to reduce the cost to the minimum, right? And if you don't reduce the cost to the minimum, it's not ideal, right? So therefore, in gradient descent, you can think of moving down this loss function as minimizing the loss to the point where it's ideal. And that's the goal of all linear models. Just an interesting note, there's also multidimensional gradient descent. This is optimization via gradient descent, which is possible in higher dimensions. So x, y, z, and dimensions of 4 dimensions, 5 dimensions, etc. So what I'm basically trying to get at is that gradient descent is a very broad optimization algorithm. It can be used to minimize any function by iteratively moving down that function in the steepest descent with the negative gradient. So gradient descent is possible for higher functions and for multidimensional vectors as well. Let's take a closer look at gradient descent and the types of gradient descent and why gradient descent is really important for the learning process. Let's go a little deeper. Let's talk about hyperparameters. What are hyperparameters? Hyperparameters are really just knobs that we tweak in machine learning algorithms. The learning rate is an example, and I'll just get to the learning rate in a second, but talking more about hyperparameters, what do I mean by knob? When machine learning engineers are basically tinkering with algorithms and trying to find the loss minimal point for a linear model, for example, they constantly tweak these hyperparameters. And by knobs, what I'm saying is that they basically do, as we talked about earlier with the trial and error process, they basically are going to make tweaks to different parameters to find this loss minimum in the fastest way possible. So coming back here, the hyperparameters are the actual knobs that we adjust. So now let's talk about the learning rate. So going back to our example of gradient descent, you may be wondering how we choose by how much to jump to the next point in gradient descent, right? How do we start from our starting point and go to the next point? And how, in other words, how do we know how much distance to travel to the next point? This is a hyperparameter known as the learning rate. And the learning rate is really what we just multiply by the gradient descent by to get to the next point. And the learning rate is, in the simplest terms possible, is how fast you want to move down the loss function in order to get to the loss minimal point. And the learning rate is a very crucial hyperparameter because in the long run, we want to get exactly to a loss minimum point of our loss function in the most efficient way possible. So learning rate has to be treated really precisely as a knob, because if you have too high of a learning rate, we might overshoot the loss minimum point. If we have too low of a learning rate, it will take forever to get the loss minimum point. So therefore, the learning rate is an example of a hyperparameter, or a knob that we tweak in machine learning algorithms, that's very crucial to the success of the gradient descent optimization algorithm. Let's talk about two types of gradient descent: stochastic gradient descent and batch gradient descent. These topics are a little bit beyond the scope of these videos, but we can still definitely discuss it. So stochastic gradient descent is a very popular version of gradient descent that uses one training example for each run. What's the advantage of stochastic gradient descent? It's much more faster because these oscillations allow the ability to avoid local minima. What I'm saying is that when we have oscillations and we have much more instability from using only one training example, if we, for example, find a local minima by accident, we can easily get out of it by oscillating. Because in this parabola, there's only one minima. It's the absolute minima, right? There's only one loss minimum. But if you go to a much more complex, like 3D graph, like this, there are certain local minima in this graph, right? But the goal is to find the absolute minima. And so if we oscillate by using the stochastic function, then we can find the absolute minima, even though there are definitely a few local minima in the area. What's the disadvantage of stochastic gradient descent? It is very noisy in terms of instability and very computationally expensive. Why? Because we're running one training example at a time. So you have to iterate for gradient descent over thousands or maybe even millions of training examples. So this is very inefficient on a computational basis, and thus it requires a lot of computing heavy resources. And also the oscillations are prone to extreme noise, and that may not be optimal if you're on a very high stability linear model. Let's talk about batch gradient descent. Batch gradient descent is where each step of gradient descent uses all the training examples. Why? What are the advantages of batch gradient descent? It's more efficient because there's less noise due to vectorization. What do I mean by vectorization? Vectorization is when we basically are applying all examples within a certain vector. Basically, every part of the vector is being used in our certain algorithm. And that produces less noise because it averages out amongst all the vectors possible. And that's a good thing because this means that compared to stochastic gradient descent, Batch gradient descent has much less oscillations and much less noise or random error. It's a much more stable gradient descent algorithm. But in terms of accuracy, this is the compromise or disadvantage that batch gradient descent provides. It's that the noise from oscillations might be sometimes beneficial, because like we talked about with stochastic gradient descent, noise is not always a bad thing. If you want to get out of a bad local minima that's not the absolute local minima, not the absolute minima, then we want some oscillation to get us out of that local minima. But in batch gradient descent, there's not enough noise or oscillation that we might need at times. So it may not be the most beneficial algorithm for all purposes. So what I'm getting at here is that there are two types of gradient descent, and it's important when you pick what type of gradient descent you want, it's important to really think about which trade-offs you want in your model, right? Are you more looking for a much more stable algorithm that can be more efficient in batch gradient descent? Or do you want something that's more accurate but is much more computationally expensive and noisy? So it's really just a trade-off. Let's go over a gradient descent example. Here's an example of how we adjust the learning rate to do gradient descent. Here's an example of basically too small of a learning rate. As you can see, if we have a starting point and we have a very small learning rate, it takes forever to reach our loss minimum point. And the loss minimum point is the local loss minimum of the parabola. It takes forever to reach it if you have a very small learning rate. Next is too large of a learning rate. If our learning rate is too large, then we can easily overshoot the minimum. That is not ideal at all, and if we overshoot the minimum, we're completely compromising on our accuracy of the model because we're not reaching the minimum of the loss function. So that's a bad thing. So we don't want too small of a learning rate or too large of a learning rate. And there we go. Now we have the correctly adjusted learning rate. With this correctly adjusted learning rate, we're basically following our gradient efficiently, and we will reach our loss minimum point efficiently and accurately reach at that point, which is a good thing. And the goal of all machine learning engineers when they build linear models is to adjust the learning rate, which, as we talked about earlier, is a hyperparameter, in order to get to this ideal situation where we efficiently get to our loss minimum without undershooting it or overshooting it. Let's conclude this video. Here's some of the takeaways of what we learned today. So we talked about how linear regression uses a line of best fit to predict data. The goal of all linear regression or linear models is to reduce the loss of a machine learning model. We reduce the loss by employing a gradient descent, a very popular optimization algorithm that uses a gradient or a negative gradient to reach the minimum loss point on the loss function. And we also talked about some of the more technical details of gradient descent, how hyperparameters like the learning rate, which is what we multiply by the gradient vector, how these are commonly adjusted or like knobs in order to find the optimal gradient for minimizing loss. And thank you for watching. Please make sure to drop a like and subscribe to the channel. Next video will be a tutorial with how to actually implement gradient descent and a scikit-learn linear model. So stay tuned with the series. Thank you for watching. I hope you enjoyed this video. And once again, I'm glad that you're here, and thank you.